Next is JK flip-flop. So in XR flip-flop, we found out that it has a disadvantage that when S equal to 1 and R equal to 1, it is an invalid state. So why is it an invalid state? Because Qn or Qn plus 1 and Qn bar or Qn plus 1 bar, these should be complements of each other. So in this particular case, S equal to 1, R equal to 1, my Qn plus 1 and Qn plus 1 bar are equal to 1. That is, they are not complements of each other. So it is an invalid state. We can't take that particular state. So that was the disadvantage of SR flip-flop. Moving on to the JK flip-flop. The circuit of JK flip-flop is somewhat similar to that of SR flip-flop, but slightly different. So again you have 4 NAND gates, like in the case of SR flip-flop. So instead of a 2-input NAND in the case of SR flip-flop at the input, we have a 3-input NAND. This is the clock. Yes. Here you have J, here you have K. In the place of S, you have J, and R, you have K. Then you have another input which we will connect shortly. The output of the first set of NAND gates will go to the second set of NAND gates. And like in the earlier case, you have back-to-back connected latch-like structure at the second set of NAND gates. So here only you have connection. Here you don't have a connection. So this is your Qn plus 1, or if you are taking the previous state, this will be Qn, and this is Qn plus 1 bar, and if you are taking the previous state, this will be Qn bar. Now this particular third input, that will come to Qn bar from J, and this will go to okay. So the NAND gate which is NAND gate to which J is connected, that the third input will go to Qn bar, and the NAND gate to which K is connected, that will go to Qn, or Qn plus 1 and Qn plus 1 bar. Okay, so this is the structure of a JK flip-flop. So again what you need is the truth table or the characteristic table, and in that we will again consider Qn, J, K and Qn plus 1. So this will be all the 8 states. So these are the 8 states. So we will check how. So like in the earlier case, we will be giving Qn and Qn bar, and then checking and giving the JK, then we will find out what is Qn plus 1. And from this characteristic table, we will go on to form the characteristic table or truth table of JK flip-flop without the Qn. But Qn plus 1 will be related to Qn. So first case is 0, 0, 0. So Qn previous state is 0. This is 1 and I am applying 0, 0 here. So 0, 0 means you needn't look at the other inputs. NAND gate, if it gets a 0 at the input, then irrespective of whatever is there in the other inputs, you will get a 1 at the output. So like in the earlier case, here the NAND gates, both the NAND gates are getting a 1 at the input. So we can't predict the output because if it gets a 1 at the input, you should know what is the other input. Then only you can say what is the output. So in that particular case, you have to take the output. That is the previous state. So here the previous state is 1 and here the previous state is 0. So we will find out the next state or the present state. So it is 1, 1, so it is 0, and 1, 0, it is 1. So since Qn plus 1 is 0, you'll write a 0 here. Yes. So next is, we are considering the previous state as 0 and 0, 1. So since this has a 0, here you have a 1. This has a 1. Clock is also always considered as 1. But then you have a third input. So you have to check what that is. So that is a 0. So this particular 0 comes here. That is from the previous state. So 1, 1, 0. This is again a 1. So if these two are 1s, that is these NAND gates get 1 each, then you have to see the previous state. Only then can you predict the output. So this is a 1 and this is a 0. So 1, 1, that is a 0, and 1, 0, that is a 1. So again this is a 0. Yes. Again next previous state is also 0. Next previous state is also a 0. So J is 1, K is 0. So since K has a 0, we needn't check the others. This is a 1. But since these two are 1s, clock and J is 1, you need to know what the other input is. And here it is 1. So all are 1s. So the output of this NAND gate is 0. So in this particular case, that is when one of the outputs is 0, or the latch of the latch, one of the inputs is 0, then we will decide on the output of that NAND gate first. That is these two, when you check, that is these two NAND gate inputs, one of them is 0. So you can change the output of that NAND gate first. So since this is 0, whatever be the previous output, this will be a 1. And when this becomes 1, that one will come here. And 1, 1, this will become a 0. So this becomes 1. If these two are 1s, then you have to see the previous state and then only predict the Qn plus 1. If one of these is 0, then that particular NAND gate which has 0 as the input, the output of that is the next state of that particular NAND gate is considered first, and that output goes to the input of the latch, because this has already changed. This 0 has changed to 1. Now it's the present state. So when this is the present state now, this 1 will come here, not the previous state, since this has already changed. Okay. So this is 1. Now again the previous state is 0. And input is J1, K1. So since it's 1 all over, you need to know whether the third input is 0 or 1 in order to predict the output of the first two NAND gates. So here it is a 1 and here it is a 0. So that whichever NAND gates has a 0 as the input, you'll say that this is 1. Okay, and this is all 1, so 0. And now which one will you take, this or this? Which output will you say first? The one with the 0 as the input. So this becomes 1 and this 1 will come here. That's what I meant. So 1 1, this becomes 0. So this is a 1. Next set is output is 1, that is the previous state is 1. So previous state is 1, this is 0 and input is 0 0. So this will be 1 1, you needn't check the third input. So this is 1 1, so you don't know what the next state is unless you take the previous state. So this 0 goes here and this 1 goes here, 1 goes here. So 1 NAND 0 is 1 and 1 NAND 1 is 0. So it is remaining at 1 itself. And next is again previous state is 1. Input changes to 0 1. So this output is 1. This you can't say that what the output is unless you know the third input. So 1 1 1, that becomes a 0. So which one will you take first? You'll take this one first. So this is 1 and when this changes, put that change here, otherwise you will get it wrong. So 1 1, this becomes 0. So this is 0. What you are writing here is always Qn plus 1, not Qn plus 1 bar. Again in the next also, previous state is 1. It is 1 0. So 0 means this is 1. This you can predict only if you see what the previous state is. So that is 0. So this is also 1. Since these two are 1, you have to see the previous state. That is, this is 0 and this is 1. So 1 0, that becomes a 1. 1 1, that becomes a 0. So this is 0. Last state again, it is 1. K becomes J1 K1. So you need, since all are ones here, you need to know the third input. So third input is 1 and here it's a 0. So this becomes a 1, this becomes a 0. When you get a 0, write the output first and move that output to the latch input. So this becomes 0. So this is 0. So this is a JK flip-flop. Now this is the total characteristic table of a JK flip-flop. So we will write the minimized characteristic table. So that will be J, K, Qn plus 1, 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0. So 0, 0 will be J0, K0 will be this and this. So if you check, if Qn is 0, Qn plus 1 is 0, Qn is 1, Qn plus 1 is 1. So this is Qn. 0, 1, this and this. So that is 0 always at the output. 1, 0 is this and this. So that you can see that if Qn is 0, Qn plus 1 is 1, Qn is 1, Qn plus 1 is 0. So what is it? Sorry, there is a mistake. There is a mistake. Okay, sorry. We just write the next one and then go. So there is a mistake. Okay. So last one is 0, 1, 1. 1, 1, J1, K1. So that is this one and this one. So if Qn is 0, Qn plus 1 is 1, Qn is 1, Qn plus 1 is 0. So that is Qn bar. So we made a mistake. So this is our table. We made a mistake. So I'll just check. Mistake was which one? This is correct. This is correct. This is wrong. So this we'll check once more. That is Qn is 1. So this is 0. And we are going to give 1, 0 at the input. Okay. So since this is 0, this is 1. This is 1, 1. This is 0, so that is a 1. So here you get a 1 and here you get a 0. So this is a 1 again and this is a 0 again. So which one did we get wrong? 1, 0. This is a 1. So our characteristic table was JK Qn plus 1 0 0 0 1 1 0 and 1 1. So what we got was Qn 0 1 and Qn bar. So this was a characteristic table. Characteristic table or truth table, both are the same of JK flip-flop. Flip-flop, no, standard notation is F bar F. If you write like that, that means that it's a flip-flop. Even short forms we have standard notations, so don't adopt any other notations. So next we need the characteristic equation, that is the equation for Qn plus 1 of JK flip-flop. So for that, like in the case of SR flip-flop, we will be drawing the truth table from the earlier case. Okay, this is Qn JK. From the big table we will be drawing. So I wiped it off. You can check that and write. So 0 0 is 0. 0 0, here it is 1. JK 0 1 is 0. 0 1 is 0. 1 0 is 1 and 1 1 is Qn bar. So this is 1 and this is 0. You can check from the earlier big table and write this. So this, if you simplify, it is like this. So this is the truth table for Qn plus 1, that you get as Qn bar J plus Qn K bar. So this is the characteristic equation of JK flip-flop. Now in the case of next is T flip-flop. Now what is a T flip-flop? A T flip-flop is when J equal to K. If J is equal to, in a JK flip-flop, if J is equal to K, then that is called a T flip-flop. Okay, so circuit wise, it is just the JK flip-flop like the earlier case. This is clock. This was J and this was K. Third input goes to the final output. So this is Qn plus 1 and this is Qn plus 1 bar. So J equal to K means this both are shorted and you are applying T. J equal to K equal to T is how you construct a T flip-flop. So in a JK flip-flop, you short J and K and give a single input and you call it as T. T flip-flop is also called as the toggle flip-flop. Okay, so since the circuit is similar to that of JK flip-flop, we know that in a JK flip-flop, when J equal to K means there are only two cases. That is, J equal to K equal to T means that is either 0 or 1. That is J equal to 0, K equal to 0, that is T equal to 0. J equal to 1, K equal to 1 is T equal to 1. Okay, so T and Qn plus 1. So T equal to 0 or T equal to 1. T equal to 0 means what? J equal to K equal to 0. J equal to 0, K equal to 0 was Qn. So that is same here. J equal to 1, K equal to 1 was Qn bar. So that is same here. So in this case, when T equal to 1, the output is Qn bar. So that is why you call it as a toggle flip-flop, because it is the complement of the output. Okay. Now there is another flip-flop called the D flip-flop or the delay flip-flop. D flip-flop is also constructed from JK flip-flop, that is J equal to D and K equal to D bar. This is the input which you will be giving. So where do you normally give J? Here. So J equal to D. So J you are giving as D and K you are giving as D bar. So you will note it and give here. So here you are applying D and here D bar. So there is only one input, that is D, that is complemented and given to the second. So D flip-flop means what? D is either 0 or 1. So J equal to D and K equal to D bar. So D equal to 0 means what? J equal to 0 and K equal to 1. D equal to 0 means J equal to 0 and K equal to 1. 0, 1, J 0, K 1 is what? 0. And in the second case, that is J equal to 1 and K equal to 0. D equal to 1 means J equal to 1 and D bar equal to 0, that is K equal to 0. So J1, K0 was 1. So these are the two characteristic tables of T flip-flop and D flip-flop. So T flip-flop and D flip-flop. So T is 0, 1, Qn plus 1 and this is Qn and Qn bar. So in T flip-flop, Qn plus 1 for T flip-flop is what? This is Qn and T. So 0, 1, 0, 1. So this is Qn. So you can extend this to when T equal to 0 and Qn equal to 0, Qn plus 1 is 0. And T equal to 0 and Qn equal to 1, Qn plus 1 is 1. T equal to 1 and Qn equal to 0, this is 1 and this is 0. So this will be equal to Qn bar T plus Qn T bar. And in the second case, D flip-flop, Qn and D. When D equal to 0, Qn plus 1 is 0. D equal to 1 means Qn plus 1 is 1. So Qn plus 1 equal to D itself. So these are the characteristic equations of D and T flip-flops.